let's discuss derivatives of inverse functions. So first, here's an example of a function and its inverse. I have the function f of x equals x cubed graphed. I'm highlighting it right now. I've also graphed the inverse of that function. That is f inverse is cube root of x. I'm highlighting that graph right now. So we have a function and its inverse. And the question we're trying to answer is how are the slopes of this function and its inverse related? And because when you find an inverse function, you switch the x's and y's, that means the slopes are going to be reciprocals. So on the original function, I'm looking at the point, this is actually cube root of 2 comma 2. And I can see that I have to go up, I don't know, maybe around 3 over 1. But when I look at the point on the inverse that has the x's and y's switched, now I actually have to go over 3-ish, up 1. Those slopes are reciprocals. And that's the formula I have written on the screen. To find the derivative of an inverse, it's the reciprocal of the derivative of the original function. So let's actually do an example. We have the function f of x equal 1 over x minus 1, where x is bigger than 1. And we're going to define g of x to be the inverse of that function. Let's find the derivative of the inverse at x equal 2. So to do these problems, rather than trying to learn a new formula, I actually like using implicit differentiation, which we talked about in the previous video. And I'm going to find the derivative that way, and I will see that the derivative of my inverse is the reciprocal of the derivative of the original function. So to find an inverse, we just switch the x's and y's. So if I have the function y equals 1 over x minus 1, its inverse is going to be x equal 1 over y minus 1. I can find the derivative of this implicitly. I'm going to start by rewriting that right-hand side as y minus 1 to the negative 1. That's going to allow me to use the chain rule. So derivative of x is 1. And then on the right-hand side, we're going to use the chain rule. So I brought down the negative 1, negative y minus 1 to the negative 2. And then I have to multiply by the derivative of the inside. The derivative of y minus 1 is going to be 1 times y prime. This is something that we can solve for y prime. Before I solve for y prime, I think I'm going to rewrite that negative exponent as a positive exponent. So negative y minus 1 to the negative 2 is the same as negative 1 over y minus 1 squared. Then to solve for y prime, we can multiply both sides by the negative and also the y minus 1 squared. That's going to give me negative y minus 1 squared equals y prime. So I have an expression for the derivative of this function implicitly. Now we want to find g prime of 2. I want to find the derivative of this function, this inverse, when x is 2. But my derivative is in terms of y. So I'm going to have to take that 2, x equal 2 for the inverse. I'm going to plug it into my inverse equation. 2 equals 1 divided by y minus 1. And this is something that we can solve for y. I multiplied both sides by y minus 1. That allows me to cancel out the y minus 1 on the right-hand side. I just have a 1 there. And then I did 2 times y minus 1. That's 2y minus 2. So add the 2. 2y is 3. Divide by 2. Y is 3 halves. So when x equals 2, y is 3 halves. And so finally, to get my derivative, I'm going to take y equals 3 halves and plug that into my expression for my derivative. I get negative 3 halves minus 1 squared. That's going to be negative 1/2 squared, or negative 1/4. And there's my solution. Now, what happens when you're using this implicit differentiation is you're technically finding the derivative of the original function. My original function was 1 over x minus 1. I actually found the derivative of that, and then to solve for y prime, I had to divide by that derivative. And so the derivative I have is actually the reciprocal of the derivative of the original function. So let's just take a look at a quick picture. So I have graphed, I'll highlight it, it's in red. This is the original function, y equals f of x. And then I graphed in blue, and I'll highlight that right now. That is the inverse of this function, which we call g of x. In this problem, we were trying to find the derivative of g of x, of the blue function, when x equal 2. That's the point I have highlighted on the screen. We found out that derivative, that slope, is negative 1/4. Now, the original function, when y is 2, should have a slope that is the reciprocal. That is negative 4 over 1. And I can see that happening in my graph. All right, let's do another one. We've got f of x equal x cubed plus x plus 1. And we're going to call g of x the inverse of that function. Find g prime of 1. So first thing I'm going to do is just switch my x's and y's, and then I can take the derivative implicitly. So I have x equal y cubed plus y plus 1. Derivative of x is 1. Derivative of y cubed would be 3y squared. And then there's my chain rule, or my implicit differentiation. I have to multiply by y prime. Derivative of y is just y prime. And derivative of 1 is 0. I'm going to solve this for y prime by factoring the y prime out. So 1 equals 3y squared plus 1 times y prime. And then I divide both sides by the 3y squared plus 1. So my derivative is 1 divided by 3y squared plus 1. Notice that the original function has a derivative of 3x squared plus 1. So the inverse has a derivative that is the reciprocal. I like doing these problems implicitly because, well, one, I don't have to actually remember that formula. But two, when you do it implicitly, you actually can see that your derivative is in terms of y. It's in terms of y for the inverse, which was x for the original function. And so then if we want to find g of 1, we're trying to find the derivative when x equals 1, and that's x for the inverse. So I'm going to have to plug that 1 in for x in my inverse equation. So 1 equals y cubed plus y plus 1. I'm going to set one side to 0 by minusing the 1. And then we've got a common factor of y. So if I factor out the y, I'm left with y squared plus 1. So that tells me y equals 0. Y squared plus 1 will never equal 0. It doesn't have any real solutions. So y equals 0 is the point where x is 1. And so to find my derivative, I'm going to plug y equals 0 into my expression 1 divided by 3y squared plus 1. And I end up getting 1 over 1, or 1. So my derivative of the inverse of this function is 1. Now that we know how to find derivatives of inverses, we're going to focus on derivatives of inverse trig functions. And so I'm actually going to save my next example for the next video, but feel free to move on to the derivative of inverse trig functions, I should say, if you want to see one more example. That's it for this video. Let me know if you have any questions.